Welcome back to another HVAC-Engineering-Techie channel training video. Today's training video is on electrical power distribution systems. This one will get you familiar with all the different pieces of equipment, electrical systems, how they're used, that sort of thing. So it's general equipment designed to help you get up to speed on electrical. Remember that this is the channel that talks all things HVAC and building systems related, including electrical. Really appreciate it. If you're a subscribing member, I really appreciate it. Thanks. If you're not, I'd sure like you to become one. All you have to do is press that subscribe button down below. Give me a thumbs up if you like the video. Costs you nothing. It's totally free. No one will ever bug you because you do that. It's just that Google uses that data to evaluate my videos, which keeps me on the air. So I'd really appreciate it if you do that. Thank you. All right, let's get started on electric power distribution systems. Thank you. So I want to take just a minute to go through all the electrical training videos we have so you can see which ones might be appropriate for you. D10 is electric system design. It's designed for, that video is designed for non-electrical engineers. If you're already an electrical engineer, you shouldn't need this data unless you want to spruce up on some of the stuff. It just includes how engineers basically do electrical design. It doesn't cover all the computer programs they use nowadays. This is just how you do it manually. S-12 is electric motors and drive systems. S-50 is basic electrical for commissioning. S-51, which is this video, is electric power distribution systems. S-52 is critical electrical power. 53 is electrical lighting systems. 54 is electrical safety for commissioning. CX9 is technical commissioning of electrical systems part 1. And CX10 is technical of electrical systems part 2. This is way too much stuff to put in one video, so they're fairly long videos at that, but they would have been coming up to 2 hours long. That was not going to be workable, so I had to do those. So electrical power distribution systems, what is that? Well, electrical distribution systems in a building are systems that carry the power to different aspects of the building. So you see here it comes in at a utility, power comes in, is fed into what we call the SES. That's the main entrance panel. And it will have a wiring connection, and it'll have a main switch and a meter. And then it'll go into different distribution boards or switches to provide power to the devices. Like you can see, this switch provides just to a large piece of equipment. This may be a large chiller or elevator or something. This one goes up to a high voltage lighting panel, 277, 480 volt. And then it has a transformer, goes down to 208, 120 volt panel. And then we have other panels here that feed different kinds of equipment. This is HVAC loads and plug loads. And this is just the way the panels look. This is a motor control center, basically. It's just a layout of the circuit. And we're going to look at all these pieces of equipment and what they do. So you can get a feeling for it. This shows metering. So you can have the main meter from the utility. And you can also have sub-meters if you want to do energy conservation. If you want to try to save energy in your building, you're going to have one meter here for all the mechanical loads, and another load here that's metering just these particular loads. And then you can have a meter here for the lighting. If you had a panels like this meter would capture all the lighting. This would do all these HVAC loads. But then you would have a little problem here because you have a meter here. So you've got a meter on this panel, a meter on this panel, because this is a plug load and electrical load. The whole idea of that is you want to have segregated panels that only have one load within the panel. And then you can meter that so you can tell what you're trying to do is isolate the HVAC load. That's the only one the operators can actually affect. Lighting control, they could change the schedule and affect it a little, but plug load, they can't change at all. So the only thing they can actually affect is HVAC, so we need to try to meter HVAC separately. And that's how that's done. Distribution equipment, wire and raceway systems, ground systems, backup power systems, metering systems, power management systems. That's the different main distribution systems. So utility transformers, utility connection point to the project. So it's a step down from utility voltage. Utility will be high voltage. It'll come into a utility transformer, step down to the voltage you're going to distribute through the building. They can have taps on them, like this has voltage taps, that allows you to connect to raise or lower the voltage in the transformer. Not you, but the utility can do that. Service entrance sections, main power entrance, normal location of the power meter, the utility meter. Doesn't have to be. The utility meter could be on the outside of the building somewhere. This could be in the main electrical room. So maybe located exterior to the building. Typical sizes, 1200 amp, 1600 amp, 2000 amp, 3000 amp, and 4000 amp. But 3000 amp normally now by code is the maximum amperage of a service entrance section. If you go over 3000 amps, you have to have more than one entrance section. Now you can have them all aggregated into 1 meter, but you can only have the reason is because it depends on the voltage. If you have 40 volt to 38,000 amps, that's a big entrance, big entrance. It takes a pretty good building to get up to that kind of size. But if you're feeding high voltage and you have 12,460 volts at 3,000 amps, that's a really large entrance. 4,000 amps, it's considerably more. So that's why they limit that. You can have a 6,000 amp. They make those, but I've never seen one. Main switch section provides main means of disconnects from the utility. So this is the main switch coming in from the utility power, and it allows you to drop the whole building at one time. It's also a breaker, so it will, if there's a problem, it will drop the whole building. Location of main ground fault detection and local metering. So if you have ground fault, which they normally do on the main breaker, and local metering, if you have local meters on it, it'll be there. Meter types may be volt, amp, kW, power factor, or complete power quality electronic metering. So there's all kinds of different things. Now, it used to be we didn't have electronic meters, so we did a lot of meters. We did voltage and amps, power factor meters on the outside of the panel, but nowadays it's normally just an electronic meter that does all of that in one. Distribution sections, fuse disconnect switches for panels and large loads, breaker sections for panels and smaller loads. The difference between a fuse switch and a circuit breaker is that a fuse switch can trip much faster. Breakers are slow compared to fuses. You can buy a fuse that's really fast. So on large loads and critical loads, they'll actually use a fuse. And breakers are fine. You can use breakers, but they're not as reactive as a fuse. So here's a distribution section, and these switches down here could have fuses in them. These are all, looks like they're fuse breakers, and this is circuit breakers. And you see these are big breakers, and they're all programmable, so you can go in and program and set those. You can also have smaller breaker sections, but that's the two different kinds of switches. And your electrical engineer will make a determination of which kind he wants where. Power management systems are electronic control systems for management of power systems. So they provide metering. This happens to be a substation system. Here's a output pad on a piece of switchgear, so the power monitoring system is available to see what's going on here. This is a main panel metering system. These are panel meters, and this is just an energy meter. So we'll normally see these up on the face of a gear if they're recording. If you're doing sub-meters, this would be a good sub-meter. Now, they can also be utility-grade meters, which would be a round meter like the main meter, depending on what the owner has and what needs he has for those. These are fairly inexpensive. I mean, $1,000 around. And, a utility-grade meter may be $2,000, so it's going to be a difference. Generators, emergency standby power, cogeneration power, or just backup power, 3 to 4 wire. Depends on whether they drive it ground or not. Fuel type, they might be multi-fuel. They could be natural gas. They could be fuel oil, or they could and propane and fuel oil, or dual fuel. They could do fuel oil and natural gas, or they could be exotic. Some of the exotic ones are flywheels. There's others, fuel cells. There's not many of them. Normally, those are used in real unique situations. I've seen the fuel cells be used up on remote sites, up on top of mountains, where they're powering radio systems, and they're fed with hydrogen. They're just for backup, so it's not like they need a lot of hydrogen, but that is possible. So generators come in open configuration where you can put them inside of a building, or they can be done for exterior locations. They can come with belly tanks or not belly tanks, call them day tanks. And normally they have a bigger tank underground that pumps into the day tank, but it depends. If it's a smaller generator, it may only have the day tank. Automatic transfer switches go hand in hand with a generator. Automatic switches to the emergency power source when the main power source is interrupted. Interlocks between both switches from being closed at the same time may disable non-critical loads before a switch activates. So they can have different ways of doing this and how it's interlocked. Switches are available with more than 2 power feeds for critical facilities. It can be 3 or 4 wire. And they can kind of look like the circuitry, and some of them can be full standing if they're big ones. Sometimes there can be a whole switchgear section that's an ATS. It might have 10 or 15 or 20 or 30 switches and one transfer mechanism, so they can be very, very large. And this is the way they just transfer power between the generator and the normal load when it's on emergency or standby power. UPS, which is an uninterruptible power supply, provides short-term power backup during a power interruption. They may also be used to clean the power. Sometimes they use them where they just they run off the UPS all the time because it's cleaning up the power from normal power. Normally used to provide power to computers or computer storage devices long enough to shut them down in a data save mode. So you don't have, the batteries may be there for 30 minutes or 15 minutes or something like that to give systems time to shut down. Or they may be hours, depending what they are. I've done some very, very large UPS systems that have large rooms full of batteries. They'll have an A circuit, a B circuit, and there'll be an A circuit room and a B circuit room, and then the inverters themselves are in a different room altogether because they're very large. Available as battery units or flywheel units. I've actually never seen a flywheel unit, but they do make them. Normally packaged unit size are from 500 volt amps to 750 kV, 750,000 volt amps. Larger units are available with the remote battery banks. This is for a commercial building, you can get UPSs that are real small, just a battery or two for your PC. That's not actually what I'm talking about. I'm talking about units that back up a whole system. And this would be a medium to small system. And this would normally package units from 500, and then this would be a bigger unit. And then bigger still would be one that has full battery banks remotely located. It'll have a big switch like this, but won't have battery compartments in them. So that's the UPSs. They're fun to commission, by the way. Batteries provide short-term power backup during a power interruption. Types of battery utilized are flooded lead acid, and these big batteries. These are probably 24 inches tall or 30 inches tall, 12 inches deep or so. They're normally big batteries. Flooded lead acid, the only problem with these is they're large at capacity, and 2, they do generate hydrogen. So for these battery banks, you need to have some kind of vent system that will ventilate the batteries when they're under load, so that gas doesn't build up in the building. So after flooded lead batteries, we have valve-regulated lead acid batteries. And they're valve-regulated, and that just means that they're a sealed battery, and they have a mechanism for taking care of overpressurization. Sealed unit, no hydrogen or gas generation. Then we have dry cells. And dry cells are used for small, very small systems, like you have in your house, but bigger. But these are used in a little bit larger systems, and these are used in the ones that have separate rooms for them. They may be starting to use some lithium-ion, but I haven't actually seen any of those yet. Motor control centers, centralized motor starter locations, fuse disconnect switches and starter, circuit breaker and starter. And these just have many different, some big switches, big starters, and small starter cans. These are all small starter cans, and of course they can go on to have many, many starters. That basically just allow for the motor starters to be in one place. It's really better than have a little motor starters everywhere in the building. Much better to have a motor control center, like a central plant or something. Main voltage panels, distribution circuit breakers for main voltage loads or other panels. Breaker size to protect the wire. 4-wire, 250 to 600 amp. Number of circuits, 60, 12, 20, 24, 30, and 42. Now this is distribution panels. These are normally bigger breakers that are feeding panels or feeding larger loads. Then we also have low voltage panels, distribution breakers, which is the 240, 208, and 120 volts. The breaker size, again, the wire may be single phase or three phase, 60 amp to 400 amp. Number of circuits, 6 through 84. So nowadays we can go clear to 84. And an 84 panel is a big panel. It's like a 7-foot high panel or 6'8" panel. So it has lots and lots of breakers in them. And this is normally done for lighting loads or receptacle loads that you have a whole bunch of them in an area. Step-down transformers reduce voltage from main voltage to lower distribution voltage, normally 480 to 208 volt / 120 or 240 volt to 120. And they can be different kinds of enclosures. This happens to be an open ventilated transformer. And the one thing about transformers, they do come in different efficiencies, clear up to about 95%, and they do get warm. When they're under load, they produce a lot of heat. So when you put these in a room, you need to have some way to cool the room so these don't overheat the room. Capacitor banks. So this increases power factor if you got a power problem, and they're just a bank of capacitors that store current and use it when it's needed. Transit voltage suppressors, TVSS. This equipment protection, and these mount in the panels, and they're designed to trim off that excess voltage. Panel meters record record electrical power conditions, volts, amps, kW, power factor, and more. May have KVR and harmonics also. Instantaneous and total per period. So these are regular meters, and they're like revenue grade meters, but not quite as accurate as a regular grade meter. This is a normal meter. That's where they'd go on. Sometimes you put them right in the face of a panel. Sometimes they would go in this service entrance section or distribution section, or maybe in the panel itself. Or like here's one that's in the face of a distribution panel. Electrical enclosures. That's all done by NEMA rating. So we have NEMA 1, which is general purpose, protects against contact normally and indoor only. It's kind of just an enclosure to keep people out of it. It's a general, NEMA 3R is a general purpose rain tight, normally exterior, not resistance to the hose stream. In other words, a NEMA 3R has a rain lip on the front of the cover to keep rain from coming in the door. And it's generally sealed enclosure, except the back is not sealed. So you cannot mount a 3R outside on a piece of unistrut and expect it to be rain tight. You'll need to put a piece of metal behind that so that the back is sealed. Ask me how I know. Learned that by experience. NEMA 12 is industrial dust tight exterior interior. This is a truly sealed panel. It's normally an 18 gauge and normally heavy steel, designed for industrial use. It is dust tight. NEMA 4X is waterproof and corrosion resistance. Normally it's a fiberglass or a plastic panel. Has rubber seals on the doors, so it is watertight. There are other NEMA 7, 8, 9, 10 are all hazardous atmospheres, special applications that I don't normally see. You normally see 4X and 12 and 3R and 1 is normally what you see in a job. Materials, painted steel, galvanized steel, stainless steel, and PVC is all material that a section can be made out of course. Painted steel is cheapest, galvanized steel is more expensive, stainless steel is very expensive, and PVC is only made for small panels. Accessories, locks, back panels and face panels, face frame panels. So they make panels in different configurations, and the engineer will have to specify what kind of doors you want on them. They have doors, that when you're testing a panel, you have to take the face frame off so you can get electrical instruments around the wires going to the breakers. Well, they do make panels that have two doors. They have a main door, which actually opens just to switch the breakers, and then it has a door behind that actually moves that whole front panel out of the way so you can actually get to the breakers. It's a really handy one. I don't see many of them because they're expensive, but you normally have to take the whole front panel off, which is irritating. Cooling fans, you get air conditioners. If the panel is going to be outside, it's going to get hot. They have them all the time that have these little units in them. That will keep the panel interior cool. Circuit breakers, small single-phase, small two-phase, medium three-phase, and large programmable three-phase. So you get these different molded case breakers, small, single-phase. This is a two-phase breaker. Here's a three-phase molded case breaker, this would not be these could be in a rack panel. This would be on not a rack panel. This would be on an interior of a panel. And this is a large one that sets into a switchgear. This is a programmable three-phase. Multi-case circuit breakers provide both thermal and magnetic protective trips, designed to provide quick trip for large overloads and slow trip for small overloads. Normally 2.5 times the load for 60 seconds temperature and 10 times load for 0.016, which is 1 cycle, seconds magnetic. So they do have those, the breakers all provide that kind of trip function. Fuses. Unlike breakers, fuse elements melt under overload conditions, so they must be replaced after a fault condition. Fuses are quick acting by nature, less than 0.01 second. Very fast. Fuse ratings. Class H is non-limiting up to 600 amp, fault at 10,000 amp. This is the older ratings. Class J, time delay up to 600 amps, now 200,000 amp rating, fault detection. Class K, current at 600 amp, 200,000 amp. Type L up to 6,000 amps, faults 200,000 amps. Now this is that largest section I was telling you about. Class R, time delay, uses up to 600 amp, fault 500% of rating. Class T, compact, quick acting up to 600 amp, fault 200,000 amps. And these are the different kinds of holders. If you see, this is a regular ferrule type, which goes in a couple of holders. This is a knife blade, goes in a couple of knife blade connections. And this is a bolted fuse, which is bolt. These are the bigger fuses, obviously. You know, you're not going to have a 6,000 amp look like that. It's going to be a bolted because the connections can't transfer that much amps to them. Fuses. Fuse type must match the fuse holder type, obviously. You can't put a bolted one in a ferrule holder. It's not going to work. Fuses should always be the same type, same size, by the same manufacturer in each switch. So we see it all the time. When you go into a facility, an existing facility, you look at a switch, and it'll have one bus fuse from somebody else, and a different color bus fuse, and another kind of bus fuse. And the reason that's not correct is because fuses are quick, and every fuse manufacturer is slightly different. So that means your three fuses don't really match each other. And what you'll end up getting is you'll get one leg that'll trip out and the other two won't, so you'll single phase your motors. So basically we want the fuses to all be the same, hopefully all the same age. So when you replace one fuse, you really should replace all three fuses, unless you keep them in stock, exactly the same brand. That's kind of important. And of course, there never should be anything else in a fuse holder. Can't tell you how many times I've seen a piece of copper pipe in a ferrule holder. Oh, it works fine, but it don't protect anything. That's the problem. So it needs to be what it's designed for. Fuses are available in increment down to 1/10 of an amp. This is where it's different than a circuit breaker. So 6,000 to 1, and it's X 9/10 to 1/10. So you could get them different fuse labels. Again, the different types of fuses. Motors. Normally, induction motors are used in the building industry, 1/25 horsepower to 2,000 horsepower. They go much bigger. I mean, you can get a much bigger motor, but in the building trades, we don't normally see anything near that big. I mean, normally 150 horsepower motor is a big motor in a building. You might have a bigger on an elevator, but, for a chiller, you might have, a big chiller. You can have 1,000-ton, 2,000-ton chillers, which will certainly have these big motors, but nothing else will have that kind of motor on it. Normally, induction motors are low cost, medium, and high efficiency, low and medium high voltage. Induction types, squirrel cage and wound rotor, technical terms you probably don't need to know. Class B, general purpose is what we use. Class C, high torque, low slip. We don't normally have many high torque loads. High torque would be something that has to start under load, and most of ours don't. Synchronous motors come from 300 horse to 100,000 horsepower. These synchronous motors are big motors, and they're medium and high voltage, high efficiency. The highest efficient motor you can get is a synchronous motor. Power factor modification. Now, I mentioned this before because what happens and why we have induction in our systems, why power factor? Because an induction motor, the voltage and current comes into the stator windings, and it induces onto the rotor. There's windings in the rotor, but they're not actually connected electrically. They're just the induction puts power into them and make the magnets. That's what makes the motor turns, is that induction. Well, there's a little bit of a lag because those two aren't exactly the induction takes some time, so it's a little bit of a lag in time, and that's what gives us these lagging circuits and gives us inductive circuits, which cause power factor. Well, a synchronous motor is not that way. A synchronous motor has a field windings, which have the regular AC current in them, and then the rotor has brushes putting DC current onto the rotor. And what happens is the way it's designed is that rotor is trying to catch the stator. So, as the three-phase power goes through a stator winding, it's actually moving the magnetic field in a circle. That's why the motor turns, right? So what's happening in a synchronous motor, the rotor is trying to catch the stator, and it can't do that. It'll come within just a few degrees of that. And when it does that, it is now doesn't have any induction, so the power factor is 1. And you actually, on the controls on these motors, you can actually adjust the power factor on some of them. So that is interesting. You can actually modify the power factor. Variable speed drives. Boy, we use these everywhere now. They come from 1.5 horsepower up to 900 horsepower. You don't actually need one for anything real low. You can use a different mechanism to do variable speed. Variable flow fans, variable flow pumps, designed to make constant speed motors variable speed by modulating the frequency of the power to the motor. Is used only for, if you use only for manual speed adjustment, then they got to have shaft grounds, because the VFD, when those IGBT ICE transistors are firing, they actually build up static charge on the shaft, and when that charge is enough to jump across the bearing grease, then it will micro machine the bearing. And if you have a manual adjustment where it's not adjusted a long time, it'll ruin the motor in about 3 months. So we've learned that by experience. So shaft grounds are really, you really should have a shaft ground on every single VFD motor. They don't always have it, but that's what they should have. Available for 1, 2, or 3-phase motors. Now, to tell you the truth, the way most 3-phase operations, or most VFD operations go, so you have a single-phase feed, you can put single-phase in and put 3-phase out to a 3-phase motor. That's normally the way it works. So that's a little bit different, but that's the way it works, and they work well. Conduit. Okay, EMT, which is electrical metallic tubing. That's the lightweight stuff. Slip couplings, compression couplings, interior only. They're not weatherproof. They're designed just to protect the cable. IMC is intermediate metallic conduit. It's very similar to EMT. It's a little thicker, and it uses compression fittings or threaded couplings, but normally compression fittings. Rigid conduit, on the other hand, basically looks like galvanized water pipe. It's actually conduit, but it's that thick. Threaded couplings, exterior explosion-proof ambient. So it's really for stuff that's going to be open to possible areas that would damage the cable. PVC-coated rigid. This is a special conduit that's made for wet environments. So you have a corrosive environment, you would use this PVC-coated rigid conduit. It's a bear to work with. You have to kind of peel off the PVC to thread it. Then you have to seal that back. So they're much more difficult than rigid, but they're needed if you're in a wet environment. Explosive NEMA 4X wet applications, PVC polyvinyl chloride conduit, which is a glue slip fittings, wet applications, interior only. Sun will eat them up, so it's not an exterior or underground. They can be used underground. Metal flexible conduit requires a ground bond wire, especially special slip couplings. So if you're going to use flex conduit, then you need to put a ground wire in it, because on the other systems, the metal conduit can be the ground, but on these it cannot be. Liquid tight flexible metal conduit requires special compression couplings that are designed to has enough diameter to put the PVC coating of the flex conduit into there. Now, the one thing about liquid tight is it's designed for exterior use or wet environments to keep the water out of the conduit. However, they are not UV resistant, so the sun will eventually eat the PVC coated up on it, so they actually need to be either covered or they need to be coated with a coating that protects it from UV damage, or else they won't last that long. Depends on your environment, but here where I'm at, 10 years maybe, if you don't have them coated. Conduit. Number of conductors of a given size of conduit are governed by the NEC code, Chapter 9, Tables 3A and 3B. underground duct bank, precast concrete sections with up to 4 to 24 or 6-inch conduits, normally used between manholes for major powders. They can also be 3-inch. And they look like this. They're pieces of concrete sections. You put them down, and then you have all these different banks to run them in. Wire cable type, solid or stranded, copper or aluminum. Now, aluminum is available, but we only use aluminum in really large conductors. We used to try to use it in lower ones, but that process has actually stopped because it's so hard to keep aluminum bolted connections tight. Aluminum expands and contracts much, much more than copper, and it will eventually loosen the connections. So they don't use that many more. But its ratings are 300 volts, 600 volts, 2,000 volts, all the way up to 15,000 volt cable, because you can have those different distribution systems. Now, you need to pay attention to that because there's many places you can't use 300 volt cable. And a lot of people don't know that. And so, I've caught a lot of control contractors that use 300 volt cable into a panel that has 120 volts, not allowed, because the lowest voltage cable for line voltage is 600 volt cable. Insulation thickness rated by voltage and temperature, protective cover rated by surface and temperature, size based on ampacity, temperature, and type of raceway, and length, of course. May have multiple conductors in the same protective cover. The wire designation, the first letter of the wire, A is for asbestos, M is for mineral, R is for rubber, SA is for silicon asbestos, T is thermoplastic, V is varnished cambric, X is close-linked synthetic polymer. Subsequent letters, and going to be more than one. The H is for resistance up to 75 C. HH is heat resistance up to 90 degrees C. No designation is for the 60 degrees C. W for moisture resistance, UF for direct burial, N for nylon jacket. So one thing we normally use a lot, we see a lot, is THNN, which are THHN. So we'll see heat resistance up to 90 degrees, so it can be in conduit. The lower temperatures are for free air cable. Conduits are rated normally 90 C. And this happens to be a picture of some larger cable, and it shows right on them where the printing is, what kind of wire they are. And here's a THN or THWN, 90 degrees C, so it's listed right on the cables. Wire size, the AWG American wire gauge goes from 18 gauge to 1 gauge. The smaller wire gauges are used for control wiring, low voltage wiring, 24 volt or so. But for power wiring, 18 gauge is the smallest. And normally we don't use anything below 14 on a project. And the majority of circuits are 12 gauge or bigger. And then, of course, we also go up to the 1-aught, 2-aught, 3-aught, 4-aught. Now that's kind of interesting to see what those are. These are really big wire. And then we have KMCL, which is circular mills. So the 250 MCM, you can see that this one is actually a 4-aught is 211. So the circular mill pipe, the MCM, which is 1,000 circular mills. And you can see that 250 is the lowest, and they go clear up to 1,000 MCM. But normally we don't see anything bigger than 750 on the site because of the weight. 750 MCM cable weighs 2.4 pounds per foot. So if you're trying to pull a 500-foot run or 200-foot run of 3 cables, that's seriously heavy. So what they do is they normally run maybe 2 400s instead of one 750 because it's easier to install. So these are big cables. I don't think I've ever seen 1,000. I'm sure they're all over the place. I don't think I just haven't seen them. Wire color. A wire color is code required. This is the code requiring for both U.S. and Canada. See, here's the Canadian ones. Here's the United States. So in the United States, low voltage, 120 to 208 to 240, is line 1 is black, line 2 is red, line 3 is blue if you have 3-phase, and the neutral is white. Grounds are always green. Now, in 277-480 volt in the United States, it's brown. Phase 1 is brown. Phase 2 is orange. Phase 3 is yellow. And neutral is gray. Okay, and it's green. Now, in Canada, phase 1 is red, phase 2 is black, and phase 3 is blue, and the neutral is white. Canada, isolated 3-phase is orange, brown, and yellow, and white. So they're very, very similar. But one thing I've always commented that I think electrical contractors should try to put brown on phase 1, orange in phase 2, and yellow on phase 3 and not mix them up. I've seen a lot of them where they paint it. They got 3 colors all right, but they don't pay attention to which phase they're on, which makes it a little tricky when you're trying to follow rotation. You're trying to figure out if the rotation's correct on a panel without a rotary meter. You know, you can watch a contractor that has a rotary meter, he can figure that out, but if you're just trying to figure it out on your own and the colors aren't right, then you're off. You really don't know. And of course, that's one of the tests that need to be done correctly before you start up a panel. Anyway, that's basic distribution equipment for systems. There's a lot of other stuff I didn't cover, but these are the basics. I hope that was helpful. I hope you enjoy the other electrical videos, getting up to speed on electrical. I appreciate you guys watching. Remember, if you have any questions, write them down in the comments. I will answer eventually. Thanks a lot for watching. Have a great day. I'll catch you on the next one.